Welcome to Circles and Radians. Well, you might be expecting that we're going to have like area equals pi r squared and circumference equals 2 pi r and stuff like that. And we are, but not today. Not today. I just wanted to show you a couple interesting things about circles first, and this thing called radians, which is actually a different way of measuring angles. And it kind of has to do with circles. So, okay, a couple things. Now, fun fact number one, and this is a useful fact often when you're analyzing various arrangements of things. Tangent is perpendicular to the radius. What does that say? What's a tangent? Well, a tangent, you might remember from somewhere, that's supposed to be a circle. Oh, that's ugly. Let's see if I can do a better one. That's a little better. So that's a circle. And if you draw a line anywhere that just barely touches the circle at one point only, that would be called a tangent. Now the center of the circle is here. So if you drew a radius line from the center of the circle to that point, it would be at 90 degrees. That's what this is saying. A tangent is perpendicular to the radius. Boy, that's a useful thing to keep in mind. So if you have a tangent, it's perpendicular to the radius. Now, I find this very easy to believe. If you just think of putting like a wagon on the pavement or something, and there's the axle to the wagon, and well, if you go straight down to the axle, doesn't that look like you're intersecting the ground at 90 degrees? Yeah. So this is a very true fact. Very true. It's so true that we can use it. Okay, so here's an example. Biff's looking out the window of an airplane flying at 35,000 feet above the surface of the earth. How far can he see to the horizon? Okay, well, this calculation interested me because I remember flying in an airplane looking down and I could see the whole Lake Ontario, and I was like, wow, that's a big lake and I can see the whole thing. I must be up there. So anyway, when you're up there, you can see pretty far, is what I'm trying to say. So let's draw what's going on here. Let's kind of draw the surface of the earth a little bit, something like this. So the earth is curved, right? And the earth has a certain radius, 3950 miles is what it asks us to assume here. So I'm going to try to draw that radius. I don't know if that would be the radius, but we'll just say that's the radius of the earth right there. So we got 3950 miles from there to the earth. Now Biff is up here above the earth by 35,000 feet, which roughly like 6 or 7 miles. So I'm going to be exaggerating this picture here. The plane isn't really this high. What's 7 miles? If this is almost 4,000, then that's obviously not 7. So this is definitely not to scale. Come on, eraser. I want an eraser. What's the big deal here? Okay. So, but anyway, there he is. So we can measure this, or not measure, but label this height here, 35,000 feet. Now, if you're up in that airplane looking to the horizon, that's about how far you'll see until you get to the horizon. You can't see anything that's over here, right? Because it's beyond the curvature of the earth. So that's what it means, see to the horizon. How far can he see to the horizon? So we kind of want this distance here. How far is it to the horizon? So, how are we going to solve for that? Well, when he's sighting to the horizon, doesn't that look like he's making a perpendicular there? Perpendicular to the radius of the earth? So yeah, we should be able to draw from here to the center of the earth and say that that's a 90-degree angle. It's always nice to find a 90-degree angle because then you say, hey, SOHCAHTOA and stuff. SOHCAHTOA and stuff. We're almost there, folks. So the radius of the earth, we labeled it here, is 3950 miles. Well, guess what? That's the radius of the earth too, so that's 3950 miles. So let me label that. Whoops, what'd you do? Come on, stop it. 3950 miles here. Okay. So I guess this side here would be the hypotenuse. Now the thing is, the hypotenuse is 3950 miles, and then you have to add this on. So how many miles is that anyway? Because we want to add miles to miles. So remember, 35,000 feet. Put that over 1. And then you can multiply by 1 mile has 5280 feet. And so we can convert to miles real quick here. So 35,000 divided by 5280. I was saying it was about 7 miles. Actually, it's just about, I like to carry some decimal places, 6.7 .629 or so miles. Okay, so looking at this right triangle now, I'm going to think of this as a right triangle in green, where the hypotenuse is 3956.629. And this base over here, of course, is still 3950, and we're solving for x. Actually, this is not SOHCAHTOA. This is Pythagorean theorem, for goodness sakes. We can use Pythagorean theorem, the old a squared plus b squared equals hypotenuse squared. So make sure you put the hypotenuse over here, right? That has to be the hypotenuse. And so our hypotenuse is this 3956.629 squared. So the legs can be, well, I can call that leg x squared, and I can call this leg 3950 squared. So you can kind of see what we need to do here. We need to take that 3956.629 squared, and we need to subtract the 3950 squared. And then, in order to get the square off the x, we'll have to take the square root. So that's what we got to type. Wow, this is a quicker problem than I thought. 3956.629 squared minus 3950 squared. Hit the equals button. Now hit square root of answer, and bada boom, bada bing. It's pretty far, really. 228.9-ish miles. So if you're flying at 35,000 feet, you can see 228.9 miles. I'm trying to think, how big is Lake Ontario? Was I really seeing 228.9 miles? Maybe, because Lake Ontario would have been, a piece of that 228.9 miles. Huh. If it's not that big, if Lake Ontario is bigger, then I must have been flying a little higher. But I'm not even sure how big it is. It's got to have some kind of distance to it, but I'll have to look that up someday. Anyway, that's cool. So again, I'm just showcasing this idea. A tangent is perpendicular to the radius. That's kind of a fun problem. I want to do another problem like that. Or not like that, but similar in the sense that we're going to use this idea, radius perpendicular to a tangent. What do we got here? It's kind of a machinist problem, maybe. Biff checks the angle of a 1.5-inch deep triangular groove. Now, sometimes when I'm doing these problems, I like to label stuff as I go. So this is 1.5-inch deep, so I presume they're talking about this distance here, from the top of the groove to the bottom of the groove, 1.500 inches. Okay, cool. Anyway, Biff checks the angle of a 1.5-inch deep triangle groove by shoving a 1.00-inch diameter roller. 1.00-inch diameter roller. So I'm just going to kind of mark to myself here that this thing has a, this thing has a 1.000-inch diameter. This circle does. Okay, keep reading. It protrudes 0.1 inches above the horizontal surface. Yeah, you can kind of see that it's protruding there, right? I guess I have to erase this now. But it's protruding above the surface here by about 0.1 inches. So I'm just going to label this 0.100 inches. Okay. That's nice. What's the question? The question is, find the angle of the groove. So this angle down here. Okay. Let's get some of this stuff out of the way here. Now, how are we going to get the angle of the groove? Well, need to make triangles somewhere, right? Let's do this. Let's call that the center of the roller, right? Now, I know that this is perpendicular, so that makes me think, let me see if I can use this somehow. Well, dig this. I could form a right triangle, right? Because the radius intersects at 90 degrees. That would be a nice right triangle. And this is like half of the angle that I'm looking for. So if I could figure out some sides of this triangle, I'd be able to solve for that angle. Now I can figure out this side right away. If it's a what's the roller? The roller is 1 inch diameter. So this is 0.500 inches right there. 0.500 inches right there. Okay. I could also say that this is, because this is still talking about the radius, this is 0.500 inches. Now I'm only talking about from here to here. What I really need to figure out is how far is it from here to here, because then I'll be golden. Then I'll have my two sides of the triangle there. How can I get at that? Well, I could try to bring in this information out here. Let's see now here. Well, I guess I also know that from here to here is 0.500 inches, right? It's the radius all the way around, no matter which way you point. Now it's, oh, look what we got here. Starting here, if you go all the way up to the top, how far have you gone? If you go all the way up to the top, you've gone 1.5 plus 0.1. This is 1.600. Okay, that's 1.6600 all the way to the top. Now come back down by an inch, because it's a 1-inch diameter roller, and then you can figure out what this dimension is. It must be the 1.6 minus the 1 inch. This must be 0.600. And I'm talking about, oh, let's use a different color here. From here to here is 0.600. Okay, so I don't really need that highlighted. I don't really need that highlighted. But that was pretty good. So we're just kind of walking around the diagram, finding dimensions and stuff. So this is 0.600. This is 0.500 because it's the radius. That's the radius. And the big thing, we know the radius is perpendicular to the tangent. And just knowing that fact, it was like, can we get somewhere if we draw the tangent? Or I'm sorry, draw the radius perpendicular to the tangent? And we can. I think we're ready to fly here, folks. So copy that right triangle over here someplace. So it's got a 0.500 on this side. It's got 0.5 plus 0.6. This is 1.00 on this side. We can solve for this angle here by doing a shift sine, right? The sine of that angle is opposite over hypotenuse is 0.500 over 1.100. And if you do that, what do you get? Shift sine of 0.5 divided by 1.1, right? Right. Boom. This is about a, depending how many decimal places you want to go, 27.036 degree angle. Now that's half of the groove. So the groove itself, and for the groove angle, I'm talking now about going all the way across like this, would have to be twice that. 2 times that. So I've got that on my calculator. I just say times 2, and it's 54 call it 07 degrees. 54.07 degrees. Actually, if you get one of those degree minutes seconds button, if you're a machinist, you might use this kind of thing. 54 degrees, 4 minutes, 16.98 seconds. You might call that a 17 seconds. I don't know. But yeah, it's about 54.07 degrees. Cool, right? So you can make all these various constructions, and learning to work your way around these pictures and constructions and stuff is half the fun. Well, that's just that little bit about circles. Now, I need to introduce you to something called radians. Radians is a different way of measuring angles, and I'll show you what a radian is in a minute. But first, let's make sure we can convert back and forth between radians and degrees. Here's what you need to know. Pi radians, and that really is pi as in 3.1416 thereabouts. 3.1416 radians is the same as 180 degrees. Just trust me. So let's just make sure we can convert. That says 1.75 radians. Remember how we convert? You put the 1.75 radians on top. You get ready to multiply. Now this is telling us that pi radians is the same as 180 degrees. So the radian units are going to cancel, and you're going to have degrees. Now there should be a pi button on your calculator somewhere. So 1.25, this is how you would enter this. 1.25, the 180 is on top, so you're multiplying by 180. The pi is on the bottom, so you would divide by the pi. Now if you can find the pi button, that's a good idea to use the pi button because it has like 15 decimal places of accuracy. If you don't, you can always enter 3.1416, but I see my pi button, it's right there, boom. So when I hit it, I'm getting just about 71 point, really? 1.2, oh, I entered the wrong number. I was thinking, yeah. 1.75, I entered a 1.25. My bad. So 1.75 times 180, divide by the pi button. Boom. That's better. 100.27, roughly. 100.27 degrees. 1.75 radians is the same as 100 degrees. Let's look at, well, let's come down to this one actually. We're going to go the other way. We got 112 degrees. Put it over 1. You want to convert to radians? This is what you do. You come back up to this fact and you say pi radians is the same as 180 degrees. So what I'm doing is I'm taking 112, I'm multiplying it by my pi button. I'll put it in a square so it looks like a button. And I'm dividing by 180. And what am I getting here? 112 times the pi button. 112 times the pi button. Right, here we go. Divided by 180. Boom. I've got a 1.955 radians. Okay, 112 degrees is almost 2 radians. That's an interesting fact. Now let's come back up to this example here. It says pi over 4 radians. Now, you could write it this way, pi over 4 radians over 1. But you could also write it this way. You could just say it's pi over 4 radians. This is exactly the same thing. Either way, it's pi being divided by 4, right? So I like to write it this way. And then we say, okay, get out that conversion. It was pi radians. Oh, look at this. Is 180 degrees. Okay. And the pi's are canceling and the radians are canceling. So it's 180 divided by 4. It's perfectly 45 degrees. How about that? Pi over 4 radians is the same as 45 degrees. Okay, one more. 60 degrees. 60 degrees, put it over 1. Multiply it by conversion factor. Pi radians is 180 degrees. So pi radians is 180 degrees. Now you could get out your calculator, but check this out. Doesn't 60 cancel into 180 exactly 3 times? The degrees are canceling, by the way. And so what you've got is if you don't want to put a decimal, you could just say it's pi over 3 radians. And I show you this because you kind of run into this stuff a lot, where people declare the angles, or what I want to say. They specify the angles using pi. So pi over 3 radians, pi over 4 radians. By the way, you can visualize this a little bit. It says here pi radians is 180 degrees, which means this is 180 degrees, right? That's 180 degrees, turn halfway around the circle. But you could also say, where'd it go? You could also say that this was pi radians. To spin from here and to bang a 180, you could say bang a pi. I banged a 180, I turned around. Yeah, I banged a pi, man. I banged a pi, I turned right around. So anyway, 45 degrees, you know where that is. Notice that a 45 degree would cut this into 4 equal pieces, hence pi over 4 would be the angle. Or 60 degrees if I were to do this again. Come on. If I were to do this again, pi over 3 would mean cut it into 3 equal pieces, and I think you can see that that would have to be 60 degrees. Yep. Roughly speaking, you can do this as an exercise, but 1 radian is something like 57.1-ish or so degrees. Okay, just so you have an idea. So pi over 3 is just barely over 1, so it's just barely over 1 radian. 60 degrees is barely over 1 radian. So 57 degrees. Anyway, that's how you convert back and forth. So keep this handy. Pi radians is the same as 180 degrees, which means you can use it just as we've been doing conversions all along. This little multiply and get things to cancel trick. Okay, but what is a radian? Here's where I'm going to show you what a radian really is. So here's a circle. That's the radius of the circle. And then let's say you're walking along the outer edge of the circle. We call this the arc length. Usually we use an S to stand for that. I like to make a script S so I don't think it's a 5. So that's the arc length. So when you walk a distance around the outer edge, that it's exactly the same as the radius, and that's what I'm trying to show here, is that this arc length here equals the radius here. When that's true, we say that you have just gone 1 radian of angle. That would be a 1 radian angle. So when S equals R, you've gone 1 radians. Obviously, if you've gone twice as far, which means you've gone twice as far, that would be 2 radians. And so we have this way of saying, well, theta is basically the ratio of your arc length to your radius, because if you walk 2 radiuses, then guess what? 2r over r is 2. You've walked 2 radians. Get this out of here. So actually you can use this. This has to be radians, not degrees. This is radians, not degrees. Sometimes we rearrange that formula to write it this way, but again, theta is radians, not degrees. But S is arc length, R is the radius of the circle, theta is the angle in radians. These are 2 common formulas. I'm not sure we're going to need them all that much. I'll show you how they work, but the main idea is, what's a radian? It's when you've gone 1 radius of distance along the arc here. So when S is equal to R, it's 1 radian. If S is 2R, you've gone 2 radians, and so on. It's the number of R's you've gone. So if you walk 3 radiuses around the edge, you've gone 3 radians of angle. Okay, that's what a radian is. S equals R is a radian. Okay, here we go. Just a couple examples to finish up. There's a circular garden. Okay, I'm going to try to draw more or less a circle. Has a diameter of 150 feet. Cool. Biff walks along the outside edge, subtending an angle of 110 degrees. Well, that would be 90 degrees, so a little bit more than that. So that's 110 degrees right here. Now it says the diameter is 150 feet, so that must be 75 feet here. So the question is, how far has he walked? That would be this arc length S. So we could use the formula S equals R theta, because we know the R, we want the S. It wants us to put the angle in. So this is where you have to be careful. This has to be the angle in radians. You can't plug the 110 in. This doesn't work. So first you take the 110 degrees and you convert it to radians. So remember, 180 degrees is the same as pi radians. And so you end up with, let me do that real quick, 110 times my pi button, and then divided by 180 equals, I'm getting 1.920 radians. 110 degrees is the same thing as 1.920 radians. That's what you put in the formula. So S is equal to R is 75 feet, 1.920 radians, and now we could just, well, multiply that by the 75. Boom! So that means he has walked a distance of just about 144.0 feet. 144.0 feet. Spot check it. Does that look about right to you? Yeah, sure, why not? If this is 75, then that's got to be a lot more than 75. So, yeah, I guess 144. So you could use that formula in that way. S equals R theta. S is arc length. You take the radius, and then you take the angle that you've kind of walked through. You've subtended, is what they say. I'm not a huge fan of this formula. I use it because I know the formula and I know how to use it. But you could also do it this way. You could say, well, the circumference of a circle is 2 pi r. So I'll go 2 pi times the 75 feet. I get 150 times pi, which I'll just figure out what that is. As a decimal, I mean, it's 471.24. So that's the circumference of the circle, the whole circle. Going all the way around the circle is 471.24 feet. But he doesn't go that far. He only goes a fraction of the way. What fraction? Well, he walks 110 degrees out of the 360 that he could walk. So you just take this number times 110 divided by 360. You're never going to believe what I get. I get 144.0 feet. which means you can get away from the radians and the S equals R theta formula if you want. If you keep in mind this kind of idea, you know what the circumference of the whole circle is, and 110 degrees, just make a little fraction out of it. How far around the circle did you go? Did you go the whole way? No. If you walked halfway, you'd say 180 degrees out of 360, which is a half. If you walked 1/4 of the way, you'd say 90 degrees out of 360, which is a fourth. We walked a little more than a fourth. We walked 110 out of 360 degrees. And so you just multiply the circumference times that fraction, you get the same answer either way. So I just kind of wanted to point that out, I guess. But again, you'll see this formula, so you might as well see it here first. All right. Now, this is one of my favorite problems to bring up at about this time of the course, and I'll explain why in a little bit. What's this one say? It says Biff again. In other words, the same problem as this one up here. He now cuts straight through the garden to get home. Oh, okay. I wonder if I could just make a copy of this. That would be so cool. Copy. Oh, awesome, awesome, awesome. Paste image. Look at that. Oh, it's pasted as an image, though. Oh, that might be a little hard to deal with, because that means I can't erase this. Right. Oh, well, that wasn't what I wanted. Can I click on you, please, and delete? Thank you. I'll just redraw the thing again. So the situation was, we had this circular garden, and he had walked 110 degrees around it, so we can kind of mark out 110 degrees like this. And we figured out the arc length already, but we're not being asked that this time. What we're saying is, okay, Biff has walked 110 degrees from here to here, and now he cuts straight through the garden to get home. In other words, he goes like this. So how far is that? What's the length of that line? That's the question now. So let me draw that line. Let me get my green going here. So let me draw this line, because that's the question. How far is that? If you cut right across the garden and assume you can go in a straight line and all that, how far is that? Now, ask yourself how to do that. And I'll mention now, the reason I like to bring this problem up is because it forces you to go back in time a little bit and remember something else that we've been doing. This is how you remember stuff. As you use it, you forget it just a little bit, and then you use it again, and it comes back more powerfully. Give you a hint. If that's 75, whoops, come on. Why does it do this to me? We also know that that's 75, right? Those are both radial lines. That's a hint. Here's another hint. Side angle side. Ooh, I hope that's a strong hint. Strong hint. When you have side angle side, you're talking about law of cosines. And how does that law of cosines work? It goes like this. C squared, remember, it's like a Pythagorean theorem, but with this correction term at the end, like this. And the key to using this formula correctly is to make sure the side C and the angle C are straight across from each other. So I called that an X, but if you don't mind, I'm going to call it a C now, because then I can call this my angle C, right? And then this could be my side A and this can be my side B. I could swap those back, it wouldn't matter, but the important thing is angle C and side C are located directly across the triangle from each other. So I made sure that was true. Now we can start plugging into this thing. So this is what I'm solving for, that side, that length. Well, you take the 75 here, A, square it. You take the 75 here, B, square it, minus 2 times 75 times the cosine of that angle in between there, 110 degrees. That's going to be your C squared. So if you want to do it all at once, you're going to have to type all that in your calculator, and then when you get an answer, you're going to have to hit the square root. So I invite you to do that. Make sure you can match me exactly. 75 squared plus 75 squared. Yep. Minus 2 times 75 times cosine 110. Close my parentheses. Hit my equals. I'm looking at 15,097 roughly, but I'm taking the square root of that answer to get... Oh, come on. Come on. I'm trying to be all here. 122 point, I'll just call it 9. 122.9, I guess those are feet that we're playing with, right? So that was 75, that was 70. That's 75. Doesn't that look like it should be something like 122? It's got to be less than 150, right? If you had 75 and 75, that would be 150, but you're at an angle here. So it's got to be less than 150. It's got to be more than 75. That seems entirely reasonable to me. So this is fun. I threw a lot of cosines in when you were least expecting it, didn't I? Wow. But it was a circle problem, sort of, wasn't it? Yep. Okay, so then there's this arc length problems. Those happen a lot. And we'll see some area formulas. I think that's the next lecture, but we got some area formulas coming up. That's when you'll officially see a equals pi r squared and stuff. Be able to convert between degrees and radians. Radians are just another way of measuring the angle. And this is a cute trick. It helps you solve a lot of problems. The radial line is perpendicular to a tangent. That old trick.